Welcome to lecture 9 of MCS 507, a course on mathematical, statistical, and scientific software. So the lecture of today starts kind of new with an introduction to Julia. So thus far in the first 3 weeks of the course, we have been introducing Python, and that introduction will still continue. But today I would like to introduce a more recent computational framework, and that is the programming language Julia. So I will, in this lecture, which consists in 3 parts, explain some of the generalities about Julia and why one should be excited about. In the next 2 sections, I will. So the main point is that one can use Julia to explore mathematical algorithms by remaining focused on the algorithms without having to go too deep into the programmer's details. So section 2 is mainly highlighting 2 aspects of how I have been using this. And then in the last part, I would like to investigate or provide an avenue on how you can verify the promise of Julia that it's also more efficient, better performant than pure Python. Okay, what about Julia? So Julia is important because it allows us to write efficient code easily. By easily, it depends always who you are talking to, but easier than certain other compiled languages. And I must say that at the very beginning, I was thinking that Julia was another scripting language. It is just as it gives you the look and feel of Python or MATLAB, but it is very efficient. You can generate very efficient code. The other reason why Julia is so important is that the language is targeted for mathematical computations. So there are many programming languages. Python is a very good language, but it's not targeted towards scientific computing. In a way, that's not so much a concern because it has the entire SciPy stack, but still, there are some things that Julia does better because it is primarily targeted towards scientific computing. Okay, how can you run Julia? One can run this online, so CoCalc provides a cloud platform, and you can start a Jupyter notebook. So the JU in Jupyter stands for Julia. You can launch a Jupyter notebook with a Julia kernel. If you have installed Julia, if you install Julia for the first time, you also have to install iJulia for the enhanced interface, and that will provide you with a kernel. If this kernel does not become directly visible, let me know. So there are some steps that I'm skipping here in the installation. One can run Julia as a calculator. So Julia looks very much like Python in this way. So we have the repeat eval print loop, just like in Python. so one can use Julia interactively. And one can also type in at the command prompt Julia, then the name of the program. And here I still wrote it as scripts. In this way, Julia is very convenient to use. If you are using a compiled language, then typically you have to compile your program, you have to link it against all kinds of libraries and build it essentially before you can executing it. So actually, in the last lecture, we ended with making a shared object library for Python. So that was quite involved. Julia takes also away or hides the complexities of what goes on behind the scenes. So that's another very smart thing that the Julia developers have been doing. Okay, here are 5 points on how you can learn more about Julia. There is the online website, so there is the documentation, so there is a wealth of information, so it's very easily again to get overwhelmed with the amount of information that is available to you. The second reference is a more in-depth SIAM review paper, which explains why Julia is a fresh approach. So in some sense, if you want a more academic entrance into Julia, then certainly SIAM review is good for reading. Then there is the Julia conference. So the last conference was online, but also completely free. So there was no registration fee. So in a way, the pandemic has made a lot more information freely available. So you can check out most likely many of the presentations. So that also gives you a view of what currently goes on with the language. So the fourth reference is a free book which I discovered recently. The title says it, Julia Data Science. So I came across it because I was interested in how data frames are used in Julia. So we will still later have a lecture in this course on data science, on what software to use for data science. But this book also gives a standalone introduction to Julia. It is completely free, so we have free software, free and open source. There is the equivalent for documentation. So the book is released under the Creative Commons attribution. And last and perhaps certainly not least, if you want a very general and also much more broader and much more user-friendly introduction than what I can give you, then there is this YouTube video by one of the co-developers of Julia. And the language has a promise of healing the planet. So the language comes with a lot of not only a fresh approach to numerical computing, but it has the potential to improve the way humans communicate with each other. So let's dive in. So I'm still a terminal person, so I always try to do as much as possible on the terminal. So the current version is 1.7. That's one thing I would like to indicate with this slide. The other thing is the built-in. So linear algebra is fundamental to scientific computing. It is built in. So Python has NumPy, but that you have to install separately. Julia comes with linear algebra. And what I want to indicate here is how do you do a computation in Julia? What is a normal matrix? So in a way, this lecture is a little bit too advanced already. If you are not into scientific computing, but let's illustrate this here on making a 100 by 100 matrix where the entries are normally distributed. And let's look at the eigenvalues. So the eigenvalues are the characteristic numbers for a matrix. So I truncated the output with the semicolon here. I suppress the output. I do not want to look at 100 by 100 table of floating point numbers. Okay, a Jupyter notebook is good to plotting. So here, these are the instructions so I also typed in these instructions in a Jupyter notebook. The plots package you may have to install separately. So when you type in using plots and it's not yet there, then it will prompt you, do you want to install it? In previous versions of Julia, it was giving you the instructions. Now here is just a yes or no. So we are coming from Python. So the L is the output of the eigenvalues command. And here so the output was a vector of complex numbers. Here I'm separating the real and the imaginary parts with a syntax that is, I believe, could also have been used in a Python session. And then we make a scatter plot. So how many commands did we do already? 3 on the previous slides. Here 4. And here is where we arrive. We have a nice plot. So what does it mean to be a matrix to be normal? Well, you can see for a 100 by 100 matrix, we have numbers scattered out. So we have, you could use this in a random point cloud between -10 and 10 for the real parts, and also about in the same range for the imaginary part. I must confess that the original experiment that I did was leaving off the N here. So I was making my experiment with rand. Rand will give you random numbers between 0 and 1. And then you see something kind of odd. And I will let you discover what the odd thing is. So the purpose of this first exercise is actually kind of give you a first taste of how quickly one can get into very interesting mathematical questions. So this is not a course about numerical linear algebra, and this exercise mainly asks you to describe what you see, not to explain why the difference between a matrix of normally distributed numbers gives a different plot than a matrix of positive random numbers between 0 and 1. So although if you have some inkling, so what is it that actually positive matrices are doing, and also what is it that the spectral radius is? If you can kind of explain the plot, then very good for you. But So the main point is here from this first session is that linear algebra comes with the standard library, and you can compute eigenvalues. You can do a lot more. So just check the documentation for the linear algebra module. Okay, so that was the first part, first taste. Now I will, in the second part, explain how this can be used to explore algorithms. So the algorithms come from numerical analysis. So my experience with Julia is already by using Julia in a numerical analysis course. So let me explain how it is used, how it can be used. So when one defines functions, so first of all, there is a very short syntax to define functions, even shorter than Python. But let me now focus a little bit on general functions. Then the documentation string comes before the definition. So in programming, readability is important, and it's very important that there is a documentation string even. Often, before you start thinking about the prototype, think about how you will explain what the function is doing. So before the definition is very good. Another main benefit, and that could also be one of the reasons why Julia can be more efficient than a scripting language, is that you can specify if your function works on machine floats or if it has to work on any number. So one can say from a scripting language, but hey, we cannot be more efficient because we have to make our function work for any type. So that's the main flexibility of a scripting language. Now, if you can provide the typing, then an efficient compilation can be provided in case the type is, for example, a 64-bit float. The third part is that whether we like MATLAB or not, MATLAB is still a standard in scientific computing. And the syntax from Julia borrows a lot from the convenient matrix laboratory way of working with scientific algorithms. So these are also three important points. So here is one of my. This also falls within the course. We finished off last week, had as theme arithmetic, and the convenience with Julia, how you can switch from hardware floats to arbitrary precision floats is quite striking. So in Python, again, you have to add something to it. The big floats come automatically in the standard library, and also using them. So here is a prototype for the Gram-Schmidt method that allows you to compute an orthogonal basis for your column space of the matrix. But you can give your matrix as a matrix of hardware floats, or you can give your matrix as a matrix of big floats, or of whatever precision you then fix before you call the routine. So this has great flexibility. So that was one of the first advantages that I felt that Julia had over Python. So in numerical analysis, we indeed focus on 64-bit arithmetic, but often it's good to examine the properties of numerical algorithms where we have a little bit more freedom in our numerical types. So that was one of the things that I liked. Now, what is Gram-Schmidt orthogonalization again? So here we have two vectors in blue, A1 and A2. We want to construct the green vectors, Q1, Q2, and we do this by subtracting from A1 the orthogonal projection, which is computed as V1. We subtract the orthogonal projection. And then we normalize. So we make sure that all the vectors have length 1. So if you have taken a course in linear algebra, then this picture is, or even vector calculus. So this is a picture from vector calculus. So the operations here, they are written for, they are plotted for two vectors in the plane. But the operations, so the inner product and then the computation of the V1, this works in general for any number of vectors. And also the subtraction is defined on any number of vectors. And there is the normalization. So then this most likely goes too fast, going from vector calculus to a linear algebra course. So what do? We have a matrix of columns, n space. So n, the little n here is typically larger than a k. So we have a table of numbers again. And we want to build an orthogonal basis, and this can be done by the same operation. So here you recognize the inner product again, and then we multiply the coefficients in this inner product with our basis vectors. So this is known as the Gram-Schmidt orthogonalization method. So as a side benefit, so you get your orthogonal basis, but if you store all the coefficients, you get a factorization of the matrix. So you get the QR decomposition out of this. So this is one of the algorithms to compute or also to define a QR decomposition. Okay, so I mentioned the MATLAB-like notation. So coming from Python, I always forget often the end. So here so you see 3 ends, and immediately coming from Python, this means that you could have shortened the code by 3 lines. But you get used to this. So one has to write the ends. So there is a deep copy that needs to be made. So in Python, I indicated the differences between call by references and call by value. So the matrices are actually passed by reference. If you do not make a deep copy, you will override the original matrix, and that's what we do not want to do here in this function. We want to keep the original matrix because we want to check whether q times r equals a. So we make a deep copy, so also a little bit more to keep in line with the function. So we copy and we allocate, and then we run through the columns, and we subtract from every column the orthogonal projection. So we do this in a loop. So we select each time all the rows from the column. So we have matrices. We view the matrices as entire two-dimensional tables, but with the column comma I notation, we can select one entire column from the matrix. So this is a very convenient syntax. Think about implementing this in C. then you have to think about, the C programmer has to think about the column layout of the matrix. So this is very much a column oriented algorithm. So this is taken care of. What I also would like to indicate is that we have the norm function, the to-norm. So this is provided in the linear algebra module. There is also the transpose operation. And you have the minus and the star operation that are automatically overloaded. And they work on arrays. In Python, there was kind of a thing that needed to happen. We had the array data type, but then we had the matrix class. So we had to, in Python, one makes the distinction between the data type and the layer on top of that. So here, since numerical linear algebra is so fundamental, the array data type in Julia has actually a front occupies a main position. So just like in MATLAB, the main data structure is actually an array. Okay, so this is not a course on numerical linear algebra, but what I want to indicate in this code here is that going from the 64-bit float to the big floats is actually a tiny modification. Just change the big float twice, and then we have the same algorithm, which is extremely convenient. All right, so then there is the testing. So this is still within the context of running one single program. I just want to indicate again the convenience of testing. So we have a 4x3 matrix, and we compute the residual from the QR decomposition. So we compare the norm, and now the norm is a norm of matrices. So we take the difference of A minus Q times R, and Q times R is another matrix. In numerical analysis, we typically write all our numbers with in exponential format. One has the formatted printing, and we can make that all our numbers show with 3 decimal places and in exponential format. Julia uses the interpolation, so with a dollar and then a number, you interpolate, you do string interpolation. So this comes from Perl. So this is something that I had to learn. But otherwise, I hope that Julia coming from Python or coming from MATLAB is actually not that hard a transition. So this is not a big culture shock, I hope. Okay, 2 exercises. So the exercises, if you learn something on linear algebra or numerical analysis, then great. But the purpose of these 2 exercises is mainly to get your feeling for the working with Julia, where you can very quickly start to explore interesting mathematical questions. So Gram-Schmidt method is a very basic method and quite straightforward to explain, but there is some loss of orthogonality, and you can check this by running a sufficiently large matrix. Pick a 100 by 100 matrix to begin with, and then look at the last 2 columns. So the inner product of the last 2 columns, if 2 columns are perpendicular to each other, their inner product should be 0. But you will see that depending on, and by default use the 64-bit precision, then you will see that this is not going to be exactly 0. You can also compare the first 2 vectors with the last 2 vectors. Now, in order to try to break things, so one critique on Gram-Schmidt is that while a good method to begin with, it's not unconditionally stable. So if your application requires often that one is close to singularities, so we work on matrices that are nearly singular, then the householder QR is actually recommended. But repeat, so that's another vulnerability of Gram-Schmidt method. Plus, on top of that, the householder QR is actually more efficient. But that to say that if you have ever to use a QR decomposition, use the built-in QR. So here also another exercise would have been to compare with the built-in QR. Okay. Here is another issue one can illustrate quite nicely with Julia. One can make plots. Quite early in a numerical analysis course, one examines different algorithms for computing roots, and one can reformulate the root finding problem in a fixed point iteration. Why do that? Well, a fixed point iteration immediately leads to an iterative method. So here it will be illustrated with this simple cubic polynomial x to the power 3 plus x minus 1, and we can redefine this as this fixed point iteration. So isolate the x. So if the fixed point equation is satisfied, then also the root finding problem is satisfied. Okay, we can interpret geometrically this construction. So the fixed point is where the fixed point equation, so the blue curve here, intersects the red diagonal. So how does then a fixed point iteration work? We are evaluating the function, so computing the right hand side, which is a vertical motion, and then we are going to the diagonal, so that's a horizontal motion. So our next point will be where this horizontal line intersects the diagonal. So and then we actually drop look at the x coordinates, and you can see that we have come perhaps not really that closer. But this is a great example to illustrate the notion of a cobweb diagram. And as we then say in numerical analysis, the slope of the function of the fixed point iteration at the fixed point determines the rate of convergence. So this is a great tool to introduce the speed of convergence of an iterative method. Related, and also it has a great visual representation. Now, if you want to do this by hand, as I indicated, the slope of your curve at the fixed point is going to determine your convergence speed. So if you want to do this by hand, you have to almost either be very skilled at drawing curves, and in a way nobody is actually anymore, because the slightest mistake you make in the slope will cause an entirely different behavior. Okay, what's the point now? The point is that making these cobweb plots can be done in a fairly straightforward uh, plotting script. So one can make a plot um, by sampling a function at a range. Here the range is parametric, so this was done in a function where a and b are the limits, provided also with the function g. And we can augment the plot. So the plot, so there is this exclamation point. It has a technical term which escapes me now, but one can append to a plot just like you can append to a list of numbers. So one can build very complicated plots bit by bit, or like here is done iteratively, step by step. So there are specific instructions. So here there is the vertical move. So there is the function itself, but then we have the iteration. So this is actual Julia code where one evaluates, one computes the next point from the previous point. So the x coordinates, and one adds that vertical line to it. Okay, I have no exercise on this, so I can, if you're really curious, I can point at where the code is. So I have in this lecture still about 15 minutes left, and now that's more than ample. I probably don't need that many minutes. So what is now about the efficiency? Root finding again. So let's go to something that is computationally intensive, and that's still interesting as well. Let's look again at the root finding method. So the method of Laguerre is a very nice method to compute the root of a polynomial. It's a method that uses the information of the first derivative and the second derivative. So because of that, it uses the slope and the concavity information. Its convergence is cubic, and at some point it also applies the quadratic formula. So if you are running this on a quadratic, then it just gives you in one step. Often you actually need to see you need to run it in multi-precision to appreciate or to observe the cubic convergence. So it's also actually a very good method for 64-bit precision, because one step is actually enough. Okay, what about the regions of convergence of this method? Okay, so here is a plot on the basins of attraction of the roots of unity. So, and as you can see, it's a fractal plot. But the plot is actually very boring. So you can see these sectors here. So what is the meaning of this plot? So all regions that have the same color are points that converge to the same root. So the roots of unity are all on the same circle. So here I put these smudges here on the plot. So I altered the plot a little bit. So you can see the 8 roots of unity. And then you see that the plot actually is very, very regular. Points that are close by, so this red sector here, all the dots in that red sector are going to converge to the same root. So the fractal nature becomes when you start at a point that is kind of close to the origin. So starting at the origin, then the root finder doesn't really know very well what to do, and then you see that all kinds of dots are starting to appear. It's also kind of interesting, you have these red sectors here of points that are actually closer to another root. So there is some fractal behavior still. So this is still an interesting plot to make. Now, for our purpose of testing Julia and its efficiency, This is a very computationally intensive uh, job. So for every pixel, so one has a box. So a box. So you should have said this is a complex plot. So there is I use the same interval both for the real and the interval and the imaginary parts. So there is a division. So one has somehow granularity of the plot. So how fine do you want to make the plot? And here there is the double loop. So the z naught gives you the starting point for Laguerre's method. So Laguerre's method, I gave it kind of hand wavingly, but look at Wikipedia. Wikipedia has a nice description of the method. It looks a little bit involved, but the code itself is not that long here. Okay, so I coded this up once in C, once in Python, and once in Julia. So here is then the result. So we are going to do a very fine grid. The file itself actually is quite of intensive. So 10,000 by 10,000. So 100 million calls to this function. So even for C, and the C was compiled with the full optimization flags, it took several minutes. So with the Julia program, I could do the same gridding. It takes about twice as much as time. Now it's still in the order of minutes. So now, in some sense, the comparison might not be fair to Julia because the C code uses very straightforward way of working. So the Julia program, how should I say this? So Julia still comes in with additional safeguards and checks. So in C, when something fails, you will get another number, or the program might even crash. So the C code will not be so gentle on the program if something goes wrong. But the punchline a little bit is that you can start from Python, and most likely when I coded this first up, I might have started with Julia, but then Python is very nice also because of the visualization. But in Python, my patience ran out, and I used a granularity that was much coarser. So if you so you could say this also, it's speed up, but you could also say quality up. So the plots that you can make with a pure Python computation are not as nice. Again, perhaps not so fair to Python because we have seen vectorization. Also, we have seen the linking with C code. So a Python programmer might say, well, you know what, you have already a C program. Why you don't not just link it in? But that's the same with Julia. Julia is actually a little bit more better in calling C functions. So one can still optimize also there. Okay, that was actually my last slide. So your invitation to me is to run this on your computer. So the programs are posted on the course website. Run this on the 3 versions. So for C, Python, and oops, this should have been Julia here. So JL. So if you time programs, the most honest comparison is to work with the wall clock time. But there are but I realized that within a Jupyter notebook, you may have to use other means. And also if you run this in the cloud, it might not be that that optimal. But still, you can take my word for it. So you can check this. So the claims that I made are actually verifiable because of the posted code. All right, time for me to conclude. So with Python, we can focus on the mathematical questions. We can have well-performant, efficient code. Julia comes with a linear algebra module immediately built in. Arrays are one of the prime data structure. So it comes with the ease of the scripting language, but its efficiency is close to C. So in a way, it is a very fresh approach to computing. So one should not confuse Python and Julia. So Python is a programming language. Julia is a programming language. Python is a scripting language. But from the user perspective as a mathematician, Julia is a very nice environment. So that is it. Thank you for your attention. And in this week of the course, on Wednesday, I will say something more about the ecosystem of Julia. And then on Friday, I will go into some more scientific programming with Julia. But the point of introducing Julia already now, quite early in the course, is that we can explore for our scientific softwares both Python and Julia. I should actually say that a lot of many Python packages are available also in Julia. So there is the PyCall. One does not have to abandon the scientific computation framework.